Today we're going to take a look at permutations and combinations again, but the topic that we're focusing on is 4.4 for permutations with repetition. Up until this point, we've looked at factorial notation, we've talked about fundamental counting principle, and we've also looked at what a permutation is. We've dealt with restrictions, but today we're going to be dealing specifically with repetition. Up until this point, every word arrangement that we've looked at, every grouping of objects that we've looked at, there's been no repeats, no repeated letters, no duplicate objects, but today that's going to change. So we're going to start by looking at an example here. So if we were to look at all of the ways that we could rearrange the letters in EBHS, there would be 24 different arrangements, or 4 pick 4. So if we think back to the fundamental counting principle, this is where we would have had 4 factorial ways to rearrange the letters. So that means 4 choices for the first letter, 3 choices for the second, 2 choices for the third, and 1 choice for the last one. So 4 factorial, or 4 pick 4, ultimately 24 different arrangements. But what happens if we have repeating letters? What happens if we take the letters in EBHS and we change the A to a B? So instead of EBHS, we've now got EBS, EBBS. Well, if I rearrange, or if I write out all of my arrangements, so basically I've taken that first list, and anywhere where I've seen an H, I've changed it to a B. This is now my grouping of letters. But you notice there's a lot of arrangements that are repeated. So we're going to go through and cross out all of our repeats. And in this case, just the way that the letters are arranged, we're basically crossing out every other grouping of letters. And so by crossing out every other arrangement, we have gone from 24 arrangements down to 12. So that happens because when I have EBHS and EHBS, by changing them both to Bs, both H's to Bs, I have, instead of 2 different or 2 distinct arrangements, I now have 2 identical arrangements. So instead of 2 arrangements, we have 1. So the number of different arrangements that we have is 12. So the number of different arrangements is 12. And so if we look at how that can be done mathematically, we had the original 4 factorial arrangements, but we had 2 repeating letters, so we divide by 2 factorial. 4 factorial divided by 2 factorial is 12. Okay, so notice we had 2 repeating letters, we divided by 2 factorial. Well, what if we go one step further and we change all of the H's and the S's to B's? So we have EBHS now becomes EB, EBBB. Well, now we have significantly less distinct combinations. And so we're going to go through again and cross out all of the repeats. And that leaves us with 4 distinct arrangements. So those 24 original arrangements is now just reduced to 4. So if we think back to what we did in the last question, we had 2 repeating letters, we divided by 2 factorial. Well, if we take those 4 originals, so 4 factorial, we had 3 repeating letters, divide by 3 factorial, we're going to get 4. So there's actually a formula that we can use, and that's here. So it says the following formula gives the number of permutations when there are repetitions. So if we have a certain number of objects, or n objects, and there's repeating A's, repeating B's, repeating C's, we just take that n factorial and we divide by the repeats. So this is our total here, n factorial divided by A factorial, B factorial, C factorial. These are our repeats. Now, what's important for you to know is that when you put this in your calculator, these repeats have to be in brackets if you're going to do this in one step. You can certainly figure out n factorial and figure out what the A factorial, B factorial, and C factorial is, and then divide the 2. But you can put everything in your calculator in one step as long as you remember your brackets. So let's take a look at some examples. First question here says, determine the number of permutations for the letters of the word Vancouver. So we can see there's some repeating letters. So the first thing we're going to do is figure out what are our repeats. And in this case, we have 2 V's. So if we count up our letters, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 letters. So our total goes on top, 9 factorial, divided by our repeats, 2 factorial. So 9 factorial divided by 2 factorial is 181,440. Now, what about mathematical? If we look at mathematical, we have 2 M's. We've got 3 A's. And we have 2 T's. So 2 M's, 3 A's, and 2 T's. If we total up all of our letters in mathematical, we have 12 letters. So 12 factorial divided by 2 factorial, 3 factorial, and 2 factorial. Again, it's important that you put this in brackets if you're going to put it in your calculator. So let's take a look at what that looks like in our calculator. So we're going to start off with 12 factorial. So 12 math, arrow to the left, 4 divided by, and this is where those brackets come in, 2 math, 4, 3, and 2 factorial. And so we've got 12 factorial divided by our repeats. And that gives us 19,958,400. So 19,958,400. All right, so I want you to pause the video and try a couple on your own. We've got attitude and engineering. So pause the video, try these on your own, and then come back and check your answers. All right, so we're going to take a look at attitude. We've got, in attitude, we have 8 letters, and there are 3 T's. So we're going to have 8 factorial divided by 3 factorial, and that gives us 6,720. Now, engineering's a little trickier. These ones I find easier to kind of cross off the letters as you're seeing your repeats. But if we look at the E's first, there are 3 repeating E's. So if I cross those off, those are done. Then for the N's, I have 1, 2, 3 N's. So 3 N's. The G's, there are 2 G's. And hiding there, we've got 2 I's. So this one has lots of repeating letters. Okay, but the method is still the same. So if we count up the letters in engineering, we've got 11 factorial. And our repeats are 3 E's, 3 N's, 2 G's, and 2 I's. So we've got 11 factorial divided by 3 factorial, 3 factorial, 2 factorial, 2 factorial. Again, if you're putting them in your calculator, that bottom set of numbers has to be in brackets. But if we put this in our calculator, we're going to get 277,200. All right, so we don't just look at combination of numbers. There's word problems that we can do that follow this exact same pattern. And so the first example we have here says Anthony bought a carton containing 10 mini boxes of cereal. You know, he's got to find something to do to occupy his time while we're in isolation here. So he had 3 boxes of cornflakes, 2 boxes of Rice Krispies, 1 box of Cocoa Pops, 1 box of Shreddies, and the remainder were Raisin Bran. And so over a 10-day period, Anthony decides he's going to eat the contents of 1 box of cereal each morning. He's changing up, changing things up, wants to try some new cereals. So how many different orders are possible if Anthony has Raisin Bran on the first morning? Well, the first thing we got to do is figure out how many Raisin Bran are there. So there are 10 boxes of cereal. We have 3 boxes of cornflakes, 2 boxes of Rice Krispies, 1 box of Cocoa Pops, and 1 box of Shreddies. And so that's 3, 5, 6, 7. So that must mean that there are 3 boxes of Raisin Bran if this has to add up to 10. So the question says, over a 10-day period, Anthony plans to eat the contents of 1 box of cereal each morning. But it asks you how many different orders are possible if he has Raisin Bran on the first morning. So now he's already eaten a box. So now there's only 2 Raisin Bran left, meaning there are only 9 boxes of cereal. So 9 factorial, but if we divide by our repeats, there are 3 cornflakes, 2 Rice Krispies, and 2 Raisin Bran. So this is a slight variation in that you have to consider how many Raisin Bran there were. You also have to consider that if Raisin Bran is eaten on the first morning, there's only that 1 box, so it's already out of the picture. We just have to consider the remaining 9 boxes. So we've got 9 factorial divided by 3 factorial times 2 factorial times 2 factorial gives us 15,120 possible cases or possible arrangements. Now that's a lot of different ways to eat your cereal. Some of you might still be wondering, well, why did we just take that box out? Well, we can look at it this way as well. We can say, okay, well, his first choice, he has the 3 Raisin Brans, and there's 3 repeats. Well, 3 factorial divided by 3 factorial is still 1. So it's really that 1 box the first day, or the one arrangement the first day times the remaining. So we often don't write that 1 there, but you can if that will help with understanding. All right, let's take another look at an example. So in the fall, a football team, maybe it's our Eagle Butte, our Colts team, a football team plays an 11-game schedule. How many ways can the schedule end with 6 wins, 3 losses, and 2 ties? Well, we have 11 games, so that's our total right there. But 6 wins, that's just 6 W's. Now, I know that sometimes wins can feel different depending on which team you're playing against, but ultimately a win is a win, a loss is a loss, and a tie is a tie. So there's our combination. We've got 6 wins, 3 losses, and 2 ties. So we're just taking 11 factorial, and we're dividing by 6 factorial, 3 factorial, and 2 factorial. And that will give us 4,620 ways that the schedule can have 6 wins, 3 losses, and 2 ties. All right, one more example. Again, take a look at the example, pause the video, try it on your own, and then come back and check your answer. So being in isolation here, some of our parents are giving us, or your parents maybe, are giving you some extra chores to do. Well, Josiah's been asked to go out into the garage and start getting the Christmas lights arranged. You know, can't be too early getting ready for Christmas. So Josiah was maybe a little behind and decided to wait till really late at night to go out and do this. And so he gets out to the garage and he comes across this string of lights, and none of the lights are in the sockets and everything's jumbled up. And so he doesn't want to wake anyone up, so he's trying to do this in the dark and he's fumbling around. This all sounds really realistic, right? Fumbling around, and he is trying to get those 12 lights into the 12 sockets. Well, there are 5 red lights and 7 green lights, and so we want to figure out how many ways he could put these bulbs into the sockets. And again, remember, he's doing this in the dark, so he's not actually aware of which lights are going where. Well, ultimately what we're doing is we're taking the 12 sockets, so 12 factorial, and dividing by our repeating colors. So 5 factorial, 7 factorial. And that will give us 792. Okay, so we're going to look at one more way that we can use permutations, and that's with pathway problems. And so we've got an example here, and it says 2 students are considering the following problem, and it says find the number of routes from point A to point B if the routes must always move closer to B. So no matter what, we can't do any backtracking. So Caitlin's a really visual person. I've seen this in class. She likes to draw lots of pictures, or I think so anyway. But being a visual person, Caitlin has arrived at the correct answer by tracing out all the 10 routes. She's like, I'm just going to draw them all out. And so she draws out all of these routes on a grid. And then Keeley says, I think there's got to be a better way. Can you imagine if this was like a huge grid, how many times we'd have to draw these lines? And so Keeley suggests a quicker method. And she's figured out that traveling from A to B involves moving 3 units east and 2 units south. So that means that we're going 3 units to the east and 2 units to the south. And then she says, well, if I write that out, that's EEESS. Oh, well, I know from doing factorials that just means I can count up all my letters and divide by my repeats. So if I were to do this using Keeley's method, that would mean that I have 5 factorial divided by my repeats, because essentially those 3 easts are treated like repeats. So 3 factorial, 2 factorial. And if I do that, I'm still going to get 10. And so if I were to look at this here, that's exactly what I get. I add my east and my south. 3 plus 2 is 5. So that's my total is 5 factorial. And then I divide by my repeats, 3 factorial and 2 factorial. So we're treating those easts and souths as repeats. Now there is one more way that we can do this, and this is by using Fermat's triangle. So an alternative approach, you can picture turning the box on its side, or I'll show you later on how we can just do it as it's sitting. But we can use Fermat's triangle. And so here, if we've got our pathway, this initial point here, going from A to D, there's only one way to go from A to D. And there's only one way to go from D to G. And there's only one way to go from A to C, and only one way to go from C to E. But when we go to F, there's 2 paths leading into the F. And so we take those initial amounts, the 1 and the 1, and we add them together, we get 2. Now, I wrote them on the sides here, but as I go forward, I'm going to be putting my numbers right at the junction points. So going from this point here down, there's only one way to go here, only one way to go here, and only one way to go here. Going down this way, there's only one way and one way. But when we're feeding in, because remember we're going downwards in this case, we're always going down, the 1 and the 1 leads to a 2. It kind of reminds me of a game of Plinko, if you're familiar with Price is Right, where we watch the little doohickey work its way down the grid. So 1, 1, and 2. And then here, 1 plus 2 is 3. 2 plus 1 is 3. 3 plus 3 is 6. 3 plus 1 is 4. And 6 plus 4 is 10. So if we go back to that game of Plinko, where we've got the little object that's going ding, 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 ding down, you can actually, by using permutations, figure out that the chance of winning that game is actually quite low when you start to think about all of the different ways, all the different pathways that get you down there. And so I know at some point you'll be doing a question kind of similar to that, figuring out how many ways to get to the bottom of a problem, similar to Plinko. Now, if I were to just look at this box here, I can just write out my pathways here as well. So I would have I always put a 1 right at the junction point, but you don't have to. So again, there's one way to go here, one way to go here, one way to go here. And then we're working downwards as well. Notice I'm not backtracking, so I'm always working towards the B. 1 plus 1 is 2. 2 plus 1 is 3. 2 plus 1 is 3. 3 plus 3 is 6. 3 plus 1 is 4. And 6 plus 4 is 10. So when you're doing this, you always have to make sure that the previous amounts have been calculated. So you can do this in a lot of different ways. I could work my way across or work my way down, but ultimately I have to always know what the previous numbers are. That also means there's chances for errors. If you make silly little counting errors or adding errors, that will cause you to have some mistakes. All right, so let's look at a couple examples here. First one here, it says a supervisor of the city bus department is determining how many routes there are from the bus station to the concert hall. And so notice that we have these 2 boxes with a clear junction point right there. So these are 2 completely separate rectangles. That's going to come into play when we get into the next question. So it says determine the number of routes possible if the bus must always leave or must always move closer to the concert hall. So we're going to start off by using patterns. So that's using our Fermat's triangle or using the patterning we're just going to map this all out. So I've got 1, 1, 1 all the way down. 1 plus 1 is 2, 3, 4. 1 plus 2 is 3, 6, 10. 1 plus 3 is 4, 10, 20. 4 plus 1 is 5, 15, and 35. Now, what do we do here? If we're going from the 35 to the next one, there's no new pathways introduced. So it's basically like 35 plus 0. So there's 35 here and 35 here. Coming down this way, there's no pathway coming in. So 35 plus 0 is still 35. And then we've got 35. Now, 35 and 35 is 70. 35 and 70 is 105. And 70 and 35 is 105. If we add those two together, we have 210 different pathways. So there's 210 pathways to get from the bus station to the concert hall. Okay, but again, this method can be a little bit flawed in that one silly little adding error can cause the entire question to be wrong. So there's another way that we can do that, and that's using permutations with repetition. So I'm just going to erase my work here. And we're going to look at what this would look like with permutations. So if I look at the first box there are 3 paths east and 1, 2, 3, 4 paths south. In the other other rectangle, we've got 2 paths east and 2 paths south. So we're going to treat these two boxes separately. We have to go through this point here. So this is thinking about going from the bus station to the concert hall and passing through that point. And if you remember in math, and means multiply. So we've got 3 east and 4 south. So that's a total of 7 factorial. And our repeats are 3 factorial and 4 factorial. Now, if we look at the next one there, we've got 2 east and 2 south. So that's 4 factorial on the top. And then dividing by our repeats, 2 factorial and 2 factorial. And so this one gets really messy when we're multiplying it out. So we'll go over the calculator again here. If I want to put that in my calculator, you can do this in 1 step or 2 steps. I'm going to show you both. So the first method, we go 7 factorial divided by 3 factorial, 4 factorial. And if we're doing 3 factorial, 4 factorial, you could have just as easily done 4 factorial, 3 factorial. And then 4 factorial divided by 2 factorial and 2 factorial. And so we have 35 times 6, which is 210. If you wanted to put this all in 1 step, you can certainly do that. It's just a little bit more with remembering of the brackets. So you have to close a second bracket there and then divide by your other one. Often I find it's easier just to do them separately and then divide, or multiply in this case. So obviously I made a little mistake there. So go back and check. We got 7 factorial divided by 3 factorial, 4 factorial, that's all in brackets, divided by 4 factorial. Oh, because I'm supposed to be multiplying. All right, so times, and then we get the 210. And so we have 210 as our final answer. Okay, so one last example. It says a taxi company is trying to find the quickest route during rush hour traffic from the train station to the football stadium. If you notice, this example here is different than the one above. We had 2 separate triangles with a clear junction point. Notice here there is no junction point. So it says going from the train station to the football station, but there's no specific point we have to go through. So this is an example where we're going to use patterns to solve. And we'll talk about why in a little bit here. So using patterns, we're going to write out our numbers. Again, I usually put a 1 right at the junction point. But there's only one way, and one way. And then we'll go down this way as well. 1 and 1 is 2. 2 and 1 is 3. 3 and 1 is 4. Notice there's no pathway coming in here, so the 4 just carries over. It's like 4 plus 0. 2 plus 1 is 3, 6, 10, 14. 3 plus 1 is 4, 10, 20, 34. 4 plus 1 is 5. 5 plus 10 is 15. 35 and 69. Now, coming down here, the 15 has nothing coming in, so it's like 15 plus 0 is just 15. 35 and 15 is 50. And then 69 and 50 is 119. So there are 119 pathways to get from the train station to the football station. Okay. And depending on your cab driver, he might choose the longest route. You never know. But there's 119 different ways to get there. Now, if we want to explain why, or if we want to look at this here, the question is asking why the permutations with repetitions formula doesn't work. Why can't we just say, well, there's 1, 2, 3, 4 ways east and 1, 2, 3, 4, 5 routes south. So 9 factorial over 4 factorial, 5 factorial. And the reason that we can't do that is because there's missing pieces. We don't actually have these 2 boxes here. And we don't have this box here. So you could do the 9 factorial over 4 factorial, 5 factorial, but you would have to subtract the pieces that are missing. And so when we have what I would call an overlapping set of rectangles, you're going to use the pattern problem. While you can use the subtraction, it's often more work than is needed. So with the overlapping triangles, anytime you see an overlapping triangle, you want to use your pathway. You want to use your pathways just by counting them out. So again, if you look here, there's no clear junction point versus the one here. This one you can use either method. With the overlapping, you have to use the counting method or patterns method. All right, so those are the examples that I have for you guys for today. Take a look at the assignment, try out some practice questions, and we'll see you tomorrow.